Section 11.6 is directional derivatives in the gradient vector, and we're just deepening our understanding and expanding our concepts of derivatives of functions of more than one variable. So we'll start with a function f, which is a function of two variables, x and y, and we'll talk about the directional derivative of f at x naught, y naught, and a direction u, which is a vector ab. So to graphically illustrate the situation, we've got a little figure up and right from this definition. And what we have going on here, so we have a point x naught, y naught. It's in the domain of f, and we've sketched the domain of f as this sort of arbitrary region in the xy plane. Again, this is not the graph of f because we're missing the z component, right? Z equals f of xy. We're just looking at the domain of this function. And we realize that if we want to talk about the derivative at the point x naught, y naught of the function f, that's going to be different for whatever different direction we might approach the point from, right? Or depart from the point from is a better way to think about it, perhaps, in the direction u in this case, or in any other given direction. So we have infinitely many ways we could come up with a derivative here based on this idea of a directional derivative. Now, let's think about this in a more practical context to get some idea of what's going on. This should be different for different values provided the function is non-constant. So in other words, let's pretend that this, or just assume that the domain of f, this outer border here, might be a contour line for the function. So some place where the function is constant, we could say maybe it's where f of xy equals 0. So it's a contour line k equals 0 for this, or a level set, level curve k equals 0. So it's the bottom of the mountain, basically. Now, let's assume the origin, just for example's sake, contains sort of a high point of this mountain in a topographic map. Okay, so if we're at the point x naught, y naught, and we look at the directional derivative in this direction, we'd be going downhill, right? So we'd have some negative value. And there'd be some intermediate value as well. It's not just downhill, but maybe somewhere along here where our change in elevation would be 0. We could walk a contour line or a level set of this curve from this point, and that would be like traversing the side of a mountain. And this would be a different value for a directional derivative. That would be a lesser in magnitude derivative than pointing down the hill. It would be 0 versus being negative for downhill. And then to go up towards the summit of this mountain, or towards the high point or a local maximum on this curve, we'd have maybe something in this direction. Possibly we'd have to have the actual function f to see it, or to calculate it directly. But we get an idea for what this is telling us. Based on whatever direction u we choose to take the derivative in, we'll get a different result for a non-constant function f. Okay, so this begs the definition for a directional derivative, because we'll want to check out derivatives in different directions for these functions. So that's defined with really no surprise. The directional derivative in the direction u of the function f at the point x naught, y naught is equal to the limit as h goes to 0 of, here's our difference quotient, x naught plus ha, y naught plus hb. So this is where u's components come into play in order to introduce that definition. And h is going to run to 0. We'll take the difference of f of x naught, y naught, and divide by h to complete the difference quotient. So as h runs to 0, we get something that sure looks exactly like what we used to see for derivatives in Calc 1. That we're limiting h going to 0, and the argument of this function approaches the argument of that function as h goes to 0. But this one incorporates the direction u within it with a and b. So that's our definition for it. We're going to find that there's a way to include partial derivatives, and that's below. The book works out this theorem. It's just a matter of details, essentially. But if f is a differentiable function of x and y, then it has a directional derivative in the direction of any unit vector, given arbitrary one, u equals ab. And that directional derivative is equal to, and this just gives us a formula that's not the limit difference quotient that we would use for the definition. It gives us a formula here that we can calculate directional derivatives with. So this is much more useful than the definition. It's kind of the name of the game in any calculus class. We have a definition first, and then we get a nice handy formula for computing the thing we're actually interested in. The details of that theorem are in the book. It's a pretty easy proof to see or to read through, but I'll leave it to the reader. Now let's use this. So we'll calculate the directional derivative at the given point in the direction indicated by the angle theta. So this is just a little bit not exactly what we'd expect. We're given an angle instead of a directional vector u. We'll have to come up with a directional vector based on that. Here's our function f. It's a function of two variables x and y. At the point 1, 1, in the direction theta equals pi over 6. Well, remember in polar coordinates, theta is the angle made with the positive x-axis sweeping in the counterclockwise direction. So there's a unit vector associated with pi over 6, and you just think of the unit circle, and that's how we get the vector that we're actually going to need for this. And that's root 3 over 2, 1/2. Remember, that's cosine pi over 6, sine pi over 6 for the left and right component of that vector. Any vector would do. It didn't have to be the unit vector, but we just chose that one because it's the one that's most familiar to us from the unit circle. Could have been root 3, 1, for instance. Anyway, we have a vector now representing that direction. Now we're just going to use this formula to build the directional derivative of f and the direction u that we now have given below. So the partials of f need to be calculated, and well, those can be done independently on their own, but we see right here we have partial of f with respect to xy, partial of f with respect to x, partial of f with respect to y. And we have a and b, the components of u. A is times f sub x, b is times f sub y for the formula. And we could double check that this is actually the partial derivative of f with respect to x. Yep, power rule, 3x squared times y to the 4th plus 4x cubed times y cubed. So that comes together nicely. We could do a similar check for f sub y, but we'll trust that it's correct. Now, the last thing we need to do is do this at the point 1, 1. All right, so far we've got a function of the directional derivative in the direction of this vector based on x and y. But if we're given a point 1, 1, we might as well plug that in, or we need to plug that in and figure out what the actual derivative at this point is. So this is a 1 for x, a 1 for y. That gives us an expression that looks like this. When we simplify it, we get this irrational number here. So that's a basic use of this. It's a nice clean formula. You calculate however many partials you need based on however many variables this function takes as its argument. We'll see up to 3, possibly 4 in some of the exercise problems, but it's no different than this one, only the vector will have extra components as well, and we would continue this, this line of products here. And we'll see an example of that later on. So that is basic directional derivative. Now, we'll define a tool that we're going to see quite a bit over and over. This is the gradient vector. So if we have a function f of x, y, some function of two variables, x and y, then we'll talk about its gradient vector. And its gradient vector, denoted here as nabla f, that upside down triangle is called nabla. And so nabla f, or gradient f, is more commonly used. Gradient of f of x, y is the vector function. It's the partial of f with respect to x, comma, partial of f with respect to y. Writing that in standard basis vectors, it looks like the following. The partial f with respect to x, partial f with respect to y, times ij respectively, and add it up. So two different representations. We'll use those sort of back and forth per whatever's convenient. And below we get a nice characterization. You can just check that this formula works out with the problem on the previous page or with the definition on the previous page. But it turns out that the directional derivative of f in the direction u is equal to the gradient of f dotted with the vector u. So that's a nice calculating tool right there. So we've got a cleaner way to maybe express this thing, or a more explicit way to express it. And let's use it in the problem below here. So for the function f of x, y equals y squared over x, and the point 1, 2 and the vector u equals this mess, we're asked to calculate the gradient vector of the function in part A. So let's handle that. The gradient vector for the function f of xy equals y squared x to the negative 1. We've done a nice thing for ourselves here and converted 1 over x, or x in the denominator, to x to the negative 1 power, so that we can use a power rule and keep our partial derivatives nice and clean. The partial derivative of this function with respect to x is negative y squared x to the negative 2, simply by a power rule. And similarly, of this function with respect to y, partial with respect to y is just 2y x to the negative 1. So there's our gradient of the function given in this line here. We've satisfied part A. Of course, they're having us piece this together to ultimately get the directional derivative of the function f at the point 1, 2 in direction u. Okay, next they ask us to evaluate the gradient at the given point. Okay, so this is the gradient of f at 1, 2. It's just a matter of plugging 1, 2 into the function and gradient function for f. That looks like this. The result is negative 4, 4. Okay, so this gradient vector at the point is just pointing in this direction, negative 4, 4. We'll see some more about this a little bit later on. What does that mean? The direction of this gradient vector will have some meaning to it. But if we're interested in finding the directional derivative, as we still are, then we just need to continue this and use the formula given above, with this vector negative 4, 4 that we've just come up with. So find the rate of change of f at the point in the direction of the vector u. So just as we were talking about before, this could be different based on whatever direction we might be moving in. And now what we're doing is we're modulating the direction that we're interested in by just picking this new variable u. Okay, so again, this is where we are on the mountain and what direction we might point on the mountain, and that'll tell us what our rate of change could be. If we're walking on a flat level trail that's following a level set, then that rate of change would be 0. If we're moving uphill or downhill, that would be indicated by magnitude of this derivative. Of course, we don't take the magnitude of the vector below, so that's still something to be found out later. Now, find the rate of change of f at the point in the direction of u. We're just calculating this via this formula. Gradient of f at the point 1, 2, dotted with the vector u. All I've done is factor or multiply the 1/3 through the expression of u that we were given above to get 2/3 and root 5 over 3. This is a simple dot product. Once we carry this out, we end up with a mistake down below that I should correct on the fly in the notes here. The result of a dot product is never a vector. Of course not. Fixing this looks like the following. This must have been done in some distracted state. It's the sum of these things. So easily fixed by the following. Do that. I should note that there were a lot of mistakes on exam 1 with dot products and cross products resulting in not a scalar or not a vector. Remember, a dot product always results in a scalar, and a cross product always results in a vector. Negative 8 plus 4 root 5. Knowing what these operations yield as their result in terms of maybe species or mathematical entities, or what kind of objects they really are, is crucial to knowing whether or not you've got something right. And you can catch a mistake like this one pretty quickly. Okay, so that is our directional derivative, our rate of change in the direction u for the function f at the given point. It's a little mouthful, but if we look at the notation, we kind of see it all come together cleanly. So there we are. That should be a single value here. Now, if this was positive or negative overall, that's the point I was getting at before. If this was positive or negative overall, we'd either be moving uphill or downhill, okay, based on that sign. So let's move on to 3 variables. 3 variables is very similar. We define the directional derivative at the point x0, y0, z0 of a function f of 3 variables, and the direction u equals abc as the following limit of a difference quotient as h goes to 0. no surprise, just an extension to a third component, the z component. And we follow up with a definition of the gradient vector. It's the partial of f with respect to x, then y, then z for all three components respectively. And then we can conclude something very similar as before, that the directional derivative of f and the direction u at any given point is the gradient of f dotted with the vector u. So our calculations that we just did before in two problems will extend to functions of three variables quite naturally and in a way that we would expect. So let's see one of those. And we're given a function of three variables, and we're asked for the function point and vector to calculate the gradient of the function, and below the directional derivative of the function at the point in the direction v. So part A is easy. We just calculate the gradient of this function. So we need to find the partial of f with respect to x, then y, then z for each component. The partial of f with respect to x, well, in this case, this is just a power rule times constant e to the y, so we get 1 times e to the y, plus z e to the x. Z is a constant. E to the x's derivative is e to the x, so we have z e to the x. The middle one has no function of z in it, or x in it, so in terms of partial derivatives, its derivative is 0. It's a constant function with regard to the partial x. So it falls out. Similarly, for the other two components, we get similar looking results, and this is our gradient vector boxed up here on the right. Remember, the gradient always results in a vector. The directional derivative will always result ultimately in a scalar. Okay, and that's because of the dot product that takes place. Now, calculate the directional derivative of the function at the point 0, 0, 0, and in the direction v equals 5, 1, negative 2. So that's just a matter of evaluating the gradient f at 0 and then dotting that with the vector 5, 1, negative 2, dotting it with v. Okay, this is all written in terms of the definition from the previous page on the left, or the theorem on the previous page. On the left is the directional derivative of f in the direction v at the point 0, 0, 0. Now, the result of plugging in 0, 0, 0 to this function is 1, 1, 1. The reader can check that. And dotting these two vectors gives us this string, this expression, which summing it up is equal to 3. Okay, so that's positive 3 is our directional derivative. That is our rate of change. It looks like we're increasing along the fourth variable, along the w variable. The function f has a positive directional derivative there. It's increasing. It's going up the mountain in some sense. Maybe not directly up the mountain, but up it. Okay, if it was negative, it'd be moving down. If it was 0, then we'd be moving parallel to it would be traversing the side of it with a 0 gain in elevation. Okay, so maximizing the directional derivative. And this is what I was mentioning before, that the gradient, it is a vector. It has its own direction. And what it turns out is that the gradient itself is the direction of maximum change of the function, maximum rate of change. Okay, so the maximum value of the directional derivative, du of f of x, and we're introducing a little bit of a new notation here, so let me make sure we're all familiar with what this is telling us. F of x. X is some vector. If we're talking about two-dimensional space, it could be representing xy. It could be representing xyz. And start to blur the line between vector and point here. That's just fine, but we're putting in an input to this function f that's multiple components, xy or xy and z, or xyz and t, just depending on what dimension our function takes values in. Mostly we'll see 2 and 3, the plane and 3 space. So the direction of maximum value, or the maximum value of the directional derivative is actually the magnitude of the gradient vector. So it turns out that the gradient vector of f, or the gradient of f, points in the direction of maximum change, okay? And that's by magnitude. So it could be the largest negative or it could be the smallest negative value or the largest positive value for the directional derivative of f. Okay, we'll see why this is the case in just a moment. So it occurs when u has the same direction as the gradient, is another way to rephrase this. So when u has the same direction as the gradient vector grad f of x, then we have maximized our function du f of x, okay, directional derivative of u of the function f of x. Okay, so let's find the maximum rate of change of f at the given point and the direction in which it occurs. All right, so we're given this function g of st. It's a function of two variables, and we're given a point 0, 2. So this is a point in the domain of the function, and we're interested in what its maximum rate of change is at that point 0, 2. So the first thing we'll need is the gradient of g, dg ds, and partial g with respect to t. Now that comes out to being careful about this. This is a partial with respect to t. We have to remember that s is partial with respect to s. T is a constant in this situation. So the t in the front of this function just sits still as a constant, and we differentiate e to the st as a partial. We get e to the st, and then times another factor of t, thanks to the chain rule of the partial with respect to s. So there's our extra factor of t, forming a t squared. That's component 1. And in the second component, we have a product rule. This is the partial of this function with respect to t. So derivative of the first times the second gives us e to the st, 1 times e to the st, plus, by the second part of the partial rule, the first, which is t, times the derivative of e to the st, or the second, with respect to t. Well, we get e to the st, and the chain rule of the partial derivative with respect to t of st is s, and that's where that constant, or that's where that factor comes from. So we've cleanly established our gradient of the function g. Next, we need to know what the gradient of that function is at the point 0, 2, and we arrive at 4, 1 once we plug in 0, 2 for s and t respectively. And what we're able to say in this is that this will be our maximum direction, right? If we want to know what our maximum rate of change is, we just need to find the magnitude of this vector. So we just need to find the magnitude of the gradient of the function at the point 0, 2. Well, we know what that vector is. It's 4, 1. 4 squared plus 1 squared, root all of that is square root of 17. So our maximum rate of change is square root of 17. That's in the direction of 4, 1. That's the our max rate of change occurs when we move along the vector 4, 1 when we're at the point 0, 2. So that's written down below, summarized again. And it's also expressed as a unit vector, just in case that was necessary. We've just divided both components by the magnitude, or divided the whole magnitude or vector by the magnitude of it. That's a common practice at this point in the class. So there it is. Our max rate is root 17 or in a direction 4, 1. Now, why is this the case? Okay, so basically a sketch or the intuition of the proof of the above theorem is the following. So why should the gradient be the direction of the maximum change of the directional derivative, or why should the gradient be the direction of the maximum change of the function, or the maximum value of its directional derivative? And that's really given to us by this. If we're interested in the directional derivative of f in the direction u, we know that it's written as the dot product of gradient of f dotted with our direction u. And then we know from chapter 10 that the dot product of two vectors is equal to the magnitude of the two vectors times each other times the cosine of theta, where theta is the angle between u and the gradient vector f of x. So this is that identity, or that characterization of the dot product we've used back in chapter 10. Okay, we know that this function is maximal when cosine theta is equal to 1. And that happens when theta is equal to 0. And that means that the angle between gradient f of x and u is 0, which means that these two vectors are parallel. And that's essentially it. In other words, u and gradient f of x point in the same direction, or if they were unitized or normalized to be unit vector length, they would be the same vector. So that's it. That's why the gradient of f of x has maximum value or is the maximum value of the directional derivative. And that's really given by this simple characterization we've had since chapter 10. So it's a nice intuition or discussion of where that theorem comes from. It's a decent way to remember what the gradient vector represents by that simple vector characterization. Okay, so that's section 11.6. And there are plenty of problems to work there in the textbook, so good luck with those.